Good evening, welcome back, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at families of functions. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough to teach, tough to learn concepts accessible to all my students. Tonight we're lucky to be joined by our panelist and presenter, Tom Reardon. Tom has many accolades. I'd say the biggest currently is that he's working for Texas Instruments in product strategy and development. So Tom, it's great to have you with us.
Hey Mike, how you doing?
We're expecting a large crowd, so your audio is muted. Feel free to send any questions to Tom using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. Please send all those general messages to everyone in the chat window. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try reconnecting your audio broadcast, either at the bottom or the top of your WebEx screen. At this point, Tom is going to discuss the agenda.
All right, so we've had the welcome and introductions. We're going to be talking about what this family of functions video series consist of and why was it created. What are the 14 parent functions? What are the 6 transformations? And how can these materials be easily accessed? Where can you get a list of the over 200 videos and the 370 equations that are graphed? And how can these be used by students and or teachers? That's kind of the plan.
Thanks so much, Tom. And be sure to stick around to the end because for one lucky winner tonight, we'll be doing a drawing for a T-Cube International Conference registration. So stick around for that. Tom, let me give you control. All right, Tom, you have control. Feel free to share your screen.
Okay, that should be up there then, right?
Yep, looks like a lot of families of functions.
Okay, all right, thanks, Mike. All right, so welcome everybody. I hope you all have having a great start of the new year. We're going to be talking about a topic that's very near and dear to my heart, families of functions. I know in the advertisement it says 150 plus videos, but we've added quite a few since then. I think it's probably closer to 220 videos that illustrate this. It's a completely modular course. And this is the website that has all the materials. I'd suggest not going there yet because I have lots of things to show you. And once I'm done, you can go look and I'll show you that website later on and how to use it. That's an underscore and all the letters are lowercase, so it is case sensitive. All right, as usual, those of you who've heard me speak before, love to start off with quotes. I have 2 of them. This is one of my more favorites. Some of you probably heard this from me before. I'm convinced that students can learn in more ways than I know how to teach. Okay, I'm not giving up, just realize that I have to keep finding ways. And we're hoping that these things I'm going to show you today are ways that will help your students learn another way. Another is a new quote that I found today that I really liked. You don't learn to walk by following rules. You learn by doing and by falling over. And this came from Richard Branson, the guy who started Virgin Records. All right, so with that, families of functions, let me kind of give you some background here a little bit. This is a transformation graphing modular unit. Modular means you only use what you need or want. So there's over 200 videos. If your students use one video and that helps them, that's fine. If they want to use a dozen, that's great too. It was created mainly for remote learning, but this can definitely complement in-class learning. Flipped classroom and independent study and review is needed. And I can see that being a lot like you just say, oh, you need to review horizontal transformations with parabolas. Go look at these videos right here, okay? So we show, first of all, there are 13 parent functions, and we show how to graph them and why they are shaped the way they are. These are as if you taught them for the very first time. So we have, those are called the parent videos, okay? And then we show how to graph those parent functions quickly, and those are called the quick videos. So capital P will stand for parent, Q for quick ones. Don't worry about memorizing any of this. And then we talk about the 6 transformations. And I like to use the phrase how the graphs are graphed by using something called a dance, or you could also use a table. We're going to look at vertical shifts, horizontal shifts, opposites of functions, vertical stretch and shrink, horizontal compressions and expansions, and also F at the opposite of X. Ooh, that went weird for me. All the materials are free and modular. You only use the parts you want or need to use. And again, flipped classroom, independent study, whatever. And lastly, it's independent of whatever graphing technology you are using. It doesn't matter if you're using 84, an Nspire, or something else. Doesn't matter. Okay, this is independent of that. So you will see a lot of my screenshots are from Nspire just because they really look good. So the 13 parent functions plus 1, a generic created piecewise function. I'm hoping that all your favorite parent functions are in here. I'm hoping none are missing. If there are, I'm sorry. If there are more than you need, don't worry about it. You just don't assign those. Okay. So these are what we call the parent functions. They are numbered that way for reference. Okay. Again, you do not memorize it. Lots of information to give you. Lots of things to share with you at the end, so don't panic. The slope and linear relations module was just completed. In fact, I have one more video to do, and so it is not on TI's website yet. However, because you are attending this webinar, you're given access to these videos before they'll be put up on the main website. Coming soon, sine, cosine, and tangent and their transformations. I'm excited about those because I taught those for many, many years. I have to give quick thank yous to the teachers that helped with this project. First of all, to Curtis Brown, former math teacher, he now works at TI. We meet about once a week, and he helps make sure things get online and all that good stuff. And then I've also had teachers from around the United States who have evaluated the videos. These are the 7 who have really been helping me since the beginning. Becky Kaysen from North Carolina, Tiffany Marion from Ohio, Don Rogers from PA. In fact, Don had his students actually use these in his calculus class. Karen Camp from Connecticut, Janelle Phillips from Massachusetts, Matt Philo from Ohio, and Miriam Santana from the great state of New York. So thank you. Also, these are the people who helped me at the beginning. Okay, and most of these people came about because they were taking either my ACT or SAT online course through TI, and I had mentioned this to them, and they were great to volunteer and help. So, and later on, if you're interested in volunteering to help, I will make that available to you. So again, thank you. Very different presentation from I normally do. I've spent over 400 hours creating these materials. I bet it's closer to 500 now to create a short video. Almost all of you have had to do that now, being online, and it takes a lot longer than just getting up there and saying it. And I created these materials to help you and your students either teach them how to graph them or learn how to graph the parent functions and their transformations. So the mathematics and pedagogy are there. Okay. One of the things that I was most proud about my pre-calculus teaching was teaching parent functions and their transformations. We made a big deal of that. So for many, many years, I taught this, and I'm now putting them into videos. I'll mainly be showing you what the materials are that are available and how to access these by you and your students, but I want to show you what they are so you can see if these are what you need or what you want. They are meant to be how a teacher would teach these concepts, allowing the student to pause and try ideas. Okay, when I'm showing you how to do something, I'm not just going to say, just do this. We're going to be talking about, looking for patterns, using a table. So I'm teaching as I'm trying to teach it. Now, that became a problem because one of the battles I was having, is it too long or too short? It's never too short. Is it too long? We'll teach students watch it. And when we field tested with students, the students would say, yeah, it's too long, but what would we cut out? Well, we really can't cut out anything. So most of the things there are essential so that they can learn, though I know they want to do it quickly. All right, so how to graph each parent function. The capital letter P is for parent function, how to graph them. They are a series of videos, length 5 to 9 minutes each, and that may sound long, but I think they're necessary. So if you see 0, 1P, that's how to graph the y equals x squared. If it's 0, 2P, it's how to graph the absolute value function, and so on. There are also key terms, intercepts, asymptotes, domain and range, and also a practical application of the graph of the parent function, or in that video. The numbers are for easy reference, and we do also have a generic function that's created with piecewise functions, and that can change. It's not always the same piecewise function. All right, so what I'm going to do is I'm going to show you 0, 1P, which is how to graph a parabola as if you'd never seen it before. But instead of playing the videos with you, which I think would just be insulting, plus also long, I'm going to show you the slides that were used to create the videos. So you're going to see the videos kind of in a fast forward, okay? And I'm going to go much faster than the video would be. I'm pretty confident you won't need to pause for understanding, but I want you to get a sense of what these are doing. But keep in mind that the videos go slower, plus students can always pause and they're encouraged to do that, okay? Remember, you can always play the videos you want to see after we're finished, okay? So let me go ahead and bring up how to graph y equals x squared. Okay, so this is, and by the way, some of you might notice I'm using Smart Notebook for my my palette here, okay, my canvas, I should say, and all of this extraneous stuff is all cut out. You just get to see the slide itself, okay? So we start off by saying you're going to need graph paper. If you need it, you can download it here and get a graph paper or a set of grids. All right, so again, I'm going to go quicker, but you'll get the sense. You'll get the idea. So y equals x squared, let's make a table. These are the 7 values for x I would like you to use. So I'll show you what 3 squared is. 3 squared is 9, and then complete the table. And often in the videos, I'll say, pause to do this, continue, resume when you're ready, okay? So after they've done that, I'll show some of the answers, say you still might need some more time, okay? If not, go ahead. And then, so here are our 7 ordered pairs. And so what we're going to do is we're going to go ahead and graph those one at a time, 3, 9, 2, 4, 1, 1, and so on. So I'll plot all 7 of those points. And what I want to do is I want them to notice something, okay? I want them to notice in the table and in the graph what's going on here. And what I'm hoping they'll notice is that this is called symmetry, and it's symmetry about the y-axis or the line x equals 0. And also, remember the first time through, students are going to say, is this a V-looking shape? Because it kind of looked like it could be a V. So to help with that, without just answering, I'll say, well, let's try 2 other values for x, like a half and negative a half. And when you square a half, you don't get 1, like unfortunately a lot of my students used to. You get 1/4. And when you square negative a half, you also get positive 1/4. And so we'll plot those 2 points. And is it a V shape? And the answer is no, it's actually more of a U-looking shape. It's rounded at the bottom. And so we're going to go ahead and connect the points and get this beautiful looking parabola, and that is the name of the curve. So some terminology I'd like them to know. The vertex is at the origin, and this mirror line is also called the axis of symmetry. And the reason for that is it's a mirror on each side of that mirror line. And then I'd like to say, anytime you go to graph this, I'd like you to think of this as a dance, as just kind of a method of doing this. So we'll start off with the origin, because 0 squared is 0, 0, 0. That's called the vertex. And then it's right 1 up 1 is the dance, because 1 squared is 1. Right 2 up 4, 2 squared is 4. And right 3 up 9, 3 squared is 9. And then we get similar on the other side. Left 1 up 1, left 2 up 4, and left 3 up 9, because the quantity of negative 3 squared is positive 9. Connect the points, and there's our, again, parabola. Again, I will point out, notice the axis of the symmetry about the y-axis. I want to make sure they kind of keep seeing that. We also want to talk about domain and range. So we'll show them this graph with a little bit of a table. And for the domain, if you look at the x-axis, every single point on the x-axis has a point either above it or on it. And so the domain is all real numbers in words, or we use the script R. The range starts at 0, including 0, and everything above that. So of all real numbers greater than or equal to 0, and we relate it that way with set notation. Where can you see parabolas in the world? Whenever we can, I've wanted to do that. So this one is from the World War II Memorial in Washington, D.C., not at the Bellagio, like many people have told me that it was. All right, so that is our parabola, how to graph it. Again, that was pretty quick. We can go slower. They can pause it. Let me stop just for a minute and check in with Mike. Mike, anything I need to know? Any questions?
So far, so good.
Okay, thank you.
Thanks.
All right, so so for the 13 parent functions, there is a how to graph them. Then we have quick graphs of each of those 13 parent functions. And these are designed to be quick. These are usually 1 to 2 minutes long, which is not very long at all, but it gets across how to graph that parent function quickly. That's the idea, okay? So let me show 2 of those, okay? This one right here is quick. Review how to graph y equals the square root of x by hand. Part of the family of functions series. Get the grid if you need it. All right, so we're going to use what I call the radical dance, and that would be something that would be talked about in the how to graph it. So we'll start with the initial point at the origin, 0, 0. And the reason for that is mentally, I'd like my students to be thinking the square root of 0 is 0, input 0, output 0. From that point, we go right 1 up 1. That's the dance, because the square root of 1 is 1. Right 4 up 2, because the square root of 4 is 2. And right 9 up 3, because the square root of 9 is 3. If I had room, I'd go right 16 up 4, but I think 4 points is enough to kind of give me the idea. So I'll go ahead and connect those points, get half of a parabola going sideways, y equals the square root of x. And that's it. That's a quick review, okay? And hopefully that's enough for most of your students who have done it before. I would not assign this as the first time. That's not going to be a good idea, I don't think. Another example I like to show would be quick review how to graph the exponential, 2 to the x, an exponential function. So here, again, we'll remind them about that. We're going to use the 2 to the x dance, which would be talked about in the parent function. So we start with the point at 0, 1. I like that to be the initial point because 2 to the 0 power is 1. 2 to the x, 0 is x, y is 1, so 0, 1. And then we'll plot everything reference to the origin, as we normally would. So I'm going to go right 1 up 2. 2 to the first is 2. Right 2 up 4, 2 squared is 4. It's almost sounding like the parabola until we get to Right 3 up 8 because 2 cubed is 8. And now when we go to the left, I like to do the right first and then the left to the positives first. So I'm going to go 2 to the negative 1, so it's going to be left 1 up a half. And I have to talk through this with students. 2 to the negative 1 means take the reciprocal of 2, which is a half. So it's going to be negative 1 up a half. Left 2 up a fourth. Remember, the negative exponents means take the reciprocal of 2 squared, which would be 1 over 4. And left 3 up 1/8, which is getting fairly close to 0. So I've got 7 points that trace out the curve. They were told that there are asymptotes that need to be drawn here. So we'll draw the asymptote of the x-axis, the line y equals 0. I'd like them to know those are interchangeable. And so we connect the points and we get the beautiful exponential curve, which we call an example of exponential growth, which means as x gets larger, y gets larger really, really fast. And that is a quick review of how to graph y equals 2 to the x. All right. So the next thing I want to talk about, we talked about the 6 transformations. I'd like to explain those a little bit so you know what to expect in the videos. They're vertical shifts. There's a video that explains that generically, why they are the way they are. And then each parent function has a quick that goes along with that, 1 or 2 of them actually that goes with them. Horizontal shifts, dilations, vertical dilations, f at the opposite of x to see whether a function's odd, even, or neither. The opposite of a function, and an f at some constant times x, which are horizontal dilations. So those are the 6. The capital letters are there mainly for me to be able to distinguish them when I made them. So there's a series of 6 videos. They're anywhere from 8 to 20 minutes. I know 20 minutes sounds like a long time, but that's what I needed to do to get the point across. And so I'm sticking with it, though I know some students won't like that. Well, you'll see. So just to give you some example of what I mean by a dilation. So here's an example of a dilation, of a vertical shift, of a horizontal shift, of a horizontal stretch or shrink, the opposite of a function, and f at the opposite of a function. Y equals the square root of the opposite of x. By the way, in my videos, I like to say opposite of x instead of negative x. Negative x gives a connotation to some students that that's always negative, and as we know that that's not true. Also, very important, each video should be viewed before doing any specific transformation graphs. For example, I should not be trying to have my students graph this if they have not done the vertical shifts video. It just won't make any sense to them. So there is an order of operations, so to speak. This is what it looks like on the website that I'll show you shortly. These are the 6, and these are what they use icons here as well as algebraic representations. There's not a y equals here. We got to fix that. All right, so I do want to show you how I developed the f of x minus h, y equals f of x minus h, quantity of x minus h with different functions to generalize that. So let me switch over. I'm going to do a shortened version of it, though it's not going to seem that short, but I am going to go a lot quicker than I would with the video. Okay, and you're not able to pause me either, unless you can get the mic to tell me to, slow down. So when we investigate the graph of y equals f at the quantity x minus h, I want to do it by hand. I want them to see it by table. I want them to be able to recognize patterns with technology, and I want them to generalize their findings in their own words before I give them to them. So that's why these videos might be a little longer. I'm still trying to teach like I normally would. So I'm going to start with our investigation y equals x squared. We have to graph using the parabola dance. I'm going to flip through this notice I say press pause until finished. So I actually tell them, do that. Now, if they don't, there's not much we can do, but I usually pause for about 3 or 4 seconds before I continue. I'm going to go through this kind of quickly because we just did this, but you can see it's very similar to what I did before. so that in case they've forgotten, this is what the parabola should look like. I remind them about the axis of symmetry, and then graph the parabola, y equals x squared. So now, keeping an eye on that parent function, we want to graph y equals the quantity x minus 4 squared. By the way, you probably have noticed my use of color. I'm really trying to use color as a teaching and learning tool here. I've been able to do that ever since I started using smartboards in the 90s. Using color is very helpful, and hopefully you're recognizing that, helping to distinguish things. All right, so I asked them to make a table with 7 rows, and I supply these x values. And the students might ask, why are these x values chosen? And I tell them, just hold on for a minute, and it should make more sense soon why I picked those for my values for x, okay? So I'm going to ask them to complete the table, pause until finished. So I'm hoping that they'll go ahead and do that. And so then I show them the answers, and I show them right next to it how that was arrived at. For example, in x is 7, 7 minus 4 is 3, 3 squared is 9, so that's there. And again, notice I'm using color here to kind of show where those values go. And now I ask them to actually plot these ordered pairs and pause till finish. So pretend they waited. And then I show them what they look like. Connect the points, and we get this beautiful looking parabola. And I want them to think about, how are these graphs similar and how are they different? But again, I don't just want to tell them. I would like them to tell themselves, and I'm hoping they will give that a shot. And so I'm hoping they'll say the graphs are the same identical shape, congruent, almost congruent. How are they different? Well, how they're different is, if you look going from blue to green, from the parent to the transformed function, it's right 4 from that point, right 4 units from that point, right 4 there, right 4 there. In fact, right 4 everywhere, okay? But what about using tables? What if I bring the table in from our y equals x squared that's in blue? How are these tables similar, and how are they different? Again, pause until you're finished. I'm hoping, I know I'm going fast, but I'm sure you get the idea. So what I'm hoping is they'll look at the y columns and say the y coordinates are identical. The x coordinates, however, if you look at those, from 3 to 7, you add 4 to 3 to get 7. You go, wait a minute. It says minus 4. Well, let's try the next one. You add 4 here. Hey, again. Oh, yeah, well, if you're going to subtract 4, that's going to move it to the left. If you have to add 4 to bring it back. So it's kind of the opposite. You're using the opposite operation, inverse operation. So all the x coordinates are increased by 4 because of the x minus 4 inside the parentheses being squared. And so it's reversed from what we thought it would be. And I'm going to address that, okay? So the coordinates are increased by 4. The y coordinates stayed the same. So I want to talk about terminology here. We say that the graph of y equal, and I want to use proper terminology, the quantity of x minus 4 squared has a horizontal shift right 4 from its parent function y equals x squared. Okay? Now I'm going to repeat the same exercise with a different equation. Now, normally I'd go through the whole thing. I'm just going to show the answer here. So think about how you would do exactly what I did before. How would you compare this to y equals x squared? What's the table look like? What's the graph look like? And so on. So I would say pause, resume when you're ready. I'm just going to go ahead right to the answer. We would build up to that, though, in the video. And it turns out that this is a horizontal shift left 3 from its parent function, and that was because of its plus 3 inside the parentheses, that quantity being squared. Again, I want them to start looking for these patterns. It's kind of opposite of what they thought it would be. So does this hold true for other functions besides y equals x squared? Because you only looked at 2, and that's really not enough to generalize quickly, but we can't spend all day either. So we're going to investigate using technology. They don't have to have technology. I'm just going to go ahead and use screenshots to show them, okay? So I did the, that's just my phone telling me I'm halfway through. So I graphed the absolute value function and showed its ordered pairs using Nspire, by the way, graph and table, and then graphed these transformations, okay? And I'm showing them what's going on. This one shifted to the, from blue to green shifted to the right one. This shifted to the right 4, right 5, left 2, left 4, okay? How about the reciprocal function? Right 2, right 3, right 4, left 1, left 3, and showing the, by the way, table values too when I can. And even a generic piecewise function, okay? And said, what is f of 1 of the quantity x minus 1? And again, the minus 1 shifted to the right 1, right 2, right 3, left 1, left 2, and so on. And so after, and they would be able to observe us much longer than I'm letting you do that now. So I'd like them to summarize what they're noticing here. What can you tell me about the graph of y equals f of the quantity x minus h, where h is some constant number? Well, if h is positive, the graph shifts right horizontally h units. And when h is negative, the graph shifts left horizontally, the absolute value of that negative number, units. And I also snuck in green for positive, red for negative, smile for positive, frown for negative. Not sure people pick up on that, but I'm into subliminal messaging. And then at the end of almost all of our videos, there's always one where it says, now you try one. And so we'll say, graph this for the practice, pause to do so, resume when you're finished to check. Now, when we do this, we don't go through the whole solution because I want to keep the videos short. We pretty much just show the answer. So there it is, okay? Y equals the square root of the quantity x plus 3. And we're hoping that that's enough to help the students along. So that is our, the only transformation we're going to be showing you. I'd love to show you other ones, but there's just not going to be time to show you the other ones and show you everything else. I will show you quick examples of these too, but before I do, let me just stop. Again, Mike, let me just check in. How we doing?
I think we're good. There's some excitement, so this is good. Thank you.
Okay, no, so I'm not the only one that's excited. Wow, that's good. Because usually in the classroom, that's it. It's just the teacher is the one that's excited. So, well, that's good. Good to hear. Thank you. All right, so so here's one. Here's graph y equals the absolute value of the quantity x minus 6 by hand 2 different ways. So you can see what I mean by 2 different ways. First is with the absolute value dance. And so normally we start at the origin on the absolute value because that's where the vertex is of that v, okay? But because of the minus 6 inside the function, we need to shift each point to the right 6 units. We've talked about this, before. And so 6, 0 is where my initial point, my vertex is going to be. And now I'll go ahead and from that point, do my absolute value dance. Not from the origin. This is like my new origin, so to speak. And so I go right 1, up 1. The absolute value of 1 is 1. Right 2, up 2. Right 3, up 3. And on the left, it's left 1, up 1, because the absolute value of a negative 1 is a positive 1. Left 2, up 2. Left 3, up 3. And I get 7 points that trace out that V fairly easily. And I connect the points. And I always like to compare it to the parent function and show that from blue to green, we're going right 6, right 6. And not just these points, but all the points on the graph are translating right 6 units. So if you prefer using a table, let's go ahead and look at a table here. So I'll write down just 5 ordered pairs just to slow it down, just to make it a little faster. And I'll do my green for the graph that I want. And I need to add 6 to each of the x coordinates because of that minus 6 inside the absolute value function. So that's what I'm going to do here in my table. I'm going to add 6 to 2, and then I keep the x, y coordinates the same. add 6 to the x's, but keep the y coordinates the same. That's what we discovered before. And so I'll plot 8, 2. 1 plus 6 is 7, keep the 1. Plot 7, comma 1. 0 plus 6 is 6, comma 0. I think you can figure out what's going on here, the rest. We have 5 points, makes our V. Go ahead and connect the points. Always like to compare it to the absolute, to the parent function, just so that they can see what's going on there. And as always, now you try one, and this one's going to be this one. Use either method or both for the practice. I encourage both, okay? And then again, once they resume, all it does is show the answer, showing that it went to the right 3 units where it normally does. Let's see where we are here. All right, so let me show one more of that. Let's look at the generic piecewise function here. How would I graph this by hand? Now this one I can't do by a dance because this isn't one I kind of memorize. There's no way I want to memorize this created function here. So we'll do it by table. And so we need to identify the key points on the graph and place the coordinates of those points into a table. So let me go ahead and do this. And so I've got -3, comma 2, -1, comma 0, 0, 1, and so on. So those are what I would call the 5 key points to trace the graph. And now I'm going to go ahead and create a second table for the function I want. And that +4 is going to make me subtract 4 from each x coordinate. That's what we've learned about horizontal shifts. And so when I subtract 4 from -3, I get -7, but I keep the y coordinate the same. And then I plot -7, comma 2. -1 minus 4 is -5, keep the 0, -5, 0, and so on. And I'll just kind of zip through. I think you can trust me on this one. And then once I have all the points, I need to connect them, but I make sure that I use the original function for the shape so that I get straight segments where there's segments, curves where there are curves, and so on. So you go ahead and connect the points. And again, I always like to compare it to the original function and show that, again, shift to the left 4 units. Now you try one, same generic function, but now f of the quantity x plus 2. Resume when you're finished to check, and again, it just shows the answer that was shifted to the left 2 units from before. All right. Unfortunately, we don't have time for some of the transformations. Opposites, I would love to show you those, the vertical dilations, odd even functions, but I assure you they're included in here, and even they're included thoroughly, okay? But we do have some time for combinations of transformations because I don't want my kids to just be able to do, one, transformation at a time. I'd like them to be able to do 2 or 3 or 4 if there are 4, could be 4. So we have 3 levels of combinations videos for each of the parent functions and each transformation. Okay, not each transformation. So CA means it's the simple one. C stands for combination. A is simple. Again, don't memorize this. CB moderate and CC complex. And here's an example of each of those. There's a simple, what we call a simple one. It has 2. This one has 3, and this one has 3 also, but a little bit harder because of the x minus 3. I think that's a tough one for students to do. So let me just illustrate with one example of that for this one. So I'd like to quickly graph this y equals 1/2 raised to the quantity x minus 2 power plus 1, 2 different ways. First way, now when we get the complicated ones, we have to decide what the parent function is and what is its shape. And so this is y equals 1/2 raised to the x power, and its shape is what I call an easy chair, okay, kind of like you sit your butt there in an easy chair. We also call this exponential decay. Think of it that way as well. But the easy chair is facing the other way. Normally 2 to the x goes the other direction. Identify the parameters, and what I mean by parameters are values in the expression that affect the graph. In this case, there are two of them, -2 and +1. And how do they affect it? The +1 shifts all the points up 1. It's outside the function, so that's a vertical shift. It also shifts up the asymptote from y = 0 to y = 1. So I'll draw that in. It also shifts the origin up. Normally the origin's at 0, 0, but that's going to affect it as well. The -2 inside the exponent there is going to shift each point to the right 2 units, which also includes the origin. So I'm going to put the new origin at over 2, up 1, and then plot it. And that's going to be kind of my starting point for drawing in the 1/2 to the x graph, okay? Notice I used origin as orange. I thought that was clever. Maybe I was the only one, but okay. So we're going to plot all the points relative to this new origin. So the first one would be like, don't go anywhere 0, but go up 1, because 1/2 raised to the 0 power is 1. Then I'm going to go right 1 up 1/2, because 1/2 raised to the first power is 1/2. From relative to that point, notice, not that ordered pair, but relative to that point. Right 2 up 1/4, because 1/2 squared is 1/4. Left 1 going the other direction up 2, because 1/2 raised to the -1, reciprocal of 1/2 is 2. And left 2 up 4, reciprocal of 1/2 is 2, and squared is 4. I didn't do the 3 or -3. Could have, just decided not to for time's sake, since they've done this many times before. So I've got the asymptote, the boundary line. I've got enough points to see where the curve is. So let's go ahead and draw it in, connect the points, and compare it to the parent function. Now, if you don't like the dance, the table, I'll do that real quickly. I'll start off with the 1/2x table that my students should know. And then the -2 is an exponent. It's going to shift each point to the right 2, which means add 2 to each x value. So let me go ahead and add 2 to each x value. And +1 is going to add 1 to each y value. So I'm going to add 1 to 1/4 and get 1 1/4 or 5/4. Now I plot 4 over 4 up 1 1/4, and so on. So I'll just go ahead and just do what it says to do, make the table, plot the 5 points. But I also need to draw the asymptote, so I have to understand, where that's going to be. And it comes from that +1 at y = 1. And then we connect the points and compare it to the parent function. All right, before I go on, Mike, it's almost 1:45. Questions, anything I should be aware of?
Yeah, just one quick one that you probably want to address from James. Question is, do you generally have students graph with technology or by hand first, and what might be some of those advantages and disadvantages?
All right, so I always first, okay, like I did y = x², did all that, but then I might bring in technology and say, let's try a few more and see that it validates that. So I like by hand first, because I think that's important for them to do that. But I like to use technology to help them notice the patterns quicker. How's that sound?
I like it.
Okay. All right. So let's go ahead and look at how to get these. And by the way, my bottom line is doing these by hand. That's the bottom line, graphing these by hand, not picking up a calculator and saying this is what it looks like. Okay. All right. So let's look at how to get these materials and a list of all the equations, graphs on videos. Let's see how we can do this here. Okay. So this is what TI's homepage looks like. We're going to go there live in a little bit. This is the bit.ly. Don't worry about that. I have links to it. That's mainly just for me. But the idea is this is to deepen the understanding of family of functions with these video courses, the 13 parent functions in detail. Right, if you go there, This is essential right here. Download the quick reference guide to all videos and materials for the course. I'll show you what that looks like. This is like, not to sound bad, but it's like the Bible here for this thing, okay? Okay, 15 minutes. So I'll show you that in a little bit. But also it says the parent function P, how to graph that. Notice there's an equal sign. The equal sign is like the icon for the parent function. The clock is, and the letter Q are the icons for quick graphs of these parent functions. And then the transformations, we have all these different transformations, including combinations of more than one transformation. So we wanted to cover all the bases as much as we could. These are the modules: quadratic, absolute value, square root, and so on. Up to 13. Again, the linear ones aren't there yet, but you're going to have access to them. Okay, I'll show you that shortly. So if you go back there and let's say you click on quadratic, it'll take you to this page, the quadratic page. Notice that the arrow is click on the arrow, on the play button, or click on the equal sign will play the parent. Will take you to YouTube and it'll play that video. If you want the quick one, you click on this link right here. If you want to download graph paper as a PDF, you can do that. Each parent function has the 6 how to graph the transformations. We thought those are essential. We don't want to send you somewhere else. We want them to be right there in your face all the time. So if you haven't done them, you can go ahead and graph them. And then these are the quick videos for each transformation, but you might say there's only 6 of them. How do you get more? You scroll for more, okay? And so these are the 15 videos for each parent function. The parent, the quick, and 13 transformations, okay? So let's go to the website and actually see it. So again, let me just take you there. You'll have plenty of time to play later on your own. I'm going to get you while I've got you. So where is it? So here we are. Here we are live at education.ti.com and so on. So you'll notice here it says download the quick reference guide. Let me download the quick reference guide, okay? And let me go ahead and open that file as a PDF, and there it is. Now it's 15 pages. I don't suggest that you print it. That's unless you want to have your own copy. This can be electronic. So the first page is a list of all the parent functions, and I created links. So let's say you wanted to go to the cube root real quickly, and you're lazy. You can go ahead and click on cube root, and it'll take you to page 7, and here's your cube root with all the stuff in it. So those are live links there, okay? At the bottom of page 1 are links to the transformation videos. And you'll notice that each one of these has 2 different links, a YouTube link and a bit.ly link. These are the same video. They just have 2 different links. The YouTube link is an awful one. The bit.ly all start off the same way. They all start off bit.ly/TI for Texas Instruments, the number 21 for the year 2021, FOF, lowercase, family of functions, and then the next thing, the last part is whatever your code is, V, or here, N, or S. Now this one for each, I have to change this to HS because H was already taken, okay? But that, we'll talk about that in a minute. So here's the squaring function. And what I wanted to have in the squaring function was what the example is that's going to be in that video, and then now you try one. And the reason I do that is if you tell your students you've got to practice the horizontal transformations for x squared, they might not have any idea what you're talking about. No offense to you or your students. But if they go over here and say, oh, I need this y equals x, this is the one I need to practice. So they're going to show me how to do this and ask me to do this one. Okay, I can do that. Or I need to do 1/2 x the quantity squared or something like that, okay? Again, 2 different links, same thing. So notice here, they all start off the same way. This one ends in 01P, ends in 01Q. And so what I'm thinking is, let's say you're making an assignment. You can say, you know what it starts off with, bit.ly whatever FOF. I want you to do 01P, 01D, 02VA. I mean, it's going to be real easy for you to make that assignment. And if you give them this link and then get this link on the website, they don't need to print it. They can just look at it and say, this is what I want. Or you can copy and paste these links into your, wherever you make your assignments online. Okay, whatever works for you, but I'm trying to make it as easy as possible for you to use these. Again, I can't emphasize enough, please give your students access to this document because they can pick and choose what they need to practice without you telling them. And you want to give them direction, but they might want to do it otherwise. So square root, reciprocal function, okay, x cubed, and so on. Okay, they're all there. Okay. All right. Where are we? 850. Okay. So, where did it go? Did I lose it? Oh, here we are. So, square root function, reciprocal function, cubic, cube root. Again, notice it's there. Let me get down to the here. So here's e to the x, not a real popular one. But notice here I have CA, CB, CC. So you can see how they get a little bit more complicated as you go down. Okay, so you can actually, this will help you when you want to make your assignments of which ones they have to do. Okay, natural log, semicircle. That's not a real popular one, but it was for me. I always like the semicircle ones. Greatest integer or step function. And then the piecewise functions, please make sure you realize not always are the piecewise functions the same shape, because I wanted them to be able to try different shapes out there. So don't count on that, okay, for those. All right. Back to the main. All right. So I did all these. By the way, the slides that I have right here are available on the website. So they are PDFs, so you can go back and have this. So don't worry about saying, oh, I didn't get good notes or whatever. They're all there. All right, so I recently completed most of the linear relations set of videos over the holidays. And the people who you saw their names on there were working over the holidays also with me, and I appreciated that very much. I have one thing left to do. They're still not posted on TI's website, but will be soon. We're hoping they'll be done by the beginning of February for the T-Cubed International Conference that's going to be virtual, that you can win free registration for that by coming here tonight. So this is the linear relations and slope. And I want to talk a little about what it is and then show it to you. But the parent function, we decided to be the standard form. So we explain how to graph that, and we do it both with table and x-intercepts and y-intercepts. And then the quick, we do quickly both ways, okay? We also treated x equals a constant there and y equals a constant there, okay? And then slope is such a big, important concept. I divided slope up into 6 parts. What does it mean? How to calculate slope from a graph. Oh, by the way, 4 flavors of slope are positive, negative, 0, and undefined. Calculate slope from tables. I show them how to derive the slope formula, how to calculate the slope from the formula, excuse me, how to draw lines with given slope. This goes back to something, a gift I created for my students 30, 40 years ago that I've now made electronic, okay? And then the summaries for these, I took one equation and graphed all 3 ways. I took 5 different equations and said graph them quickly, and then they had to decide which was the best way to do it. Point slope, slope intercept, intercepts, whatever. So let me show you that real quickly. I think I have time to take a minute to do that. So this is what it means, and it's 4 flavors. Again, I'm going to go real quickly here. It's part 1 of 6 on slope. The word slope has many descriptions. It's a number usually represented with a fraction, tells how slanted a line is. It's also described as a rate of change. We say it occurs in 4 flavors. Lines that slant uphill from left to right are said to have a positive slope. Lines that slant downhill from left to right are said to have a negative slope. Lines that are horizontal are said to have a slope of 0. 0 can be written as a fraction in several different ways. 0 divided by 1, 0 divided by 3, but not 0 divided by 0 because that's still undefined. And I wanted to address that with my students on how you write 0 as a fraction and talk about undefined. But here's how I handle the no slope. There are 4 flavors, but there's only 3 types of numbers. We've run out of numbers. So we got uphill, downhill, horizontal, and what's missing? Vertical. And so vertical is undefined. There are no numbers left. Like dividing by 0 is undefined. Ha-ha. And we say the vertical line has no slope. Then a quick review and self-assessment in here. Go ahead and pause and do this. And then I show them the answers. This is positive, slants uphill, horizontal, slants downhill, and undefined vertical. Several interpretations. Vertical change divided by horizontal change, rise over run, change in y over change in x. Sometimes we use abbreviations like the lowercase letter m. We also like to use the Greek letter delta for change in. I mean, there's all this stuff here that just could be overwhelming, okay? But I tell them, write this extended equation in your notes. Remember this. Please get this idea right here. This is a big deal. Pause is needed, resume when ready. Some real-world interpretations, rate of change. Here's some examples, miles per hour, dollars per hour. They can relate to that. Megabits per second, they can relate to that. Here are some you might recognize. Have you ever seen this one before? Parts per million. CFM, cubic feet per minute. And here are my favorite. Gallons per flush. Check your toilet. What's your gallons per flush? Unless it's LPF, liters per flush. So this is a summary page of that, okay, of that there. And where am I finishing up here? Finally, how do you and your students access these videos? One website has links to all the information right now. Write this down. Mike can put it in the chat if he wants to, bit.ly/graph_TRANSF. Lowercase, it is case sensitive. So if you go there, this is what it'll look like, okay? It looks like a mess. This is not TI's website. This is going to only be here to hold us over until we get TI's website up to speed. But the first one will actually take you, this will take you to TI's website. Actually, let me just take you there. So here it is. The second one is a one-page PDF that explains this. This is what would be essential for you, I think. You might you might want to print this, I'm not sure, but it explains to you a one-page, real quick summary, but explains a lot of stuff in one page. So I'll leave that for you. One of the things I forgot to point out, to go back to the main menu, you click the top part. Let me illustrate that. So if I go, let's say, go to absolute value, and I say I want to go back to the main menu, it's not obvious, click anywhere up here. Like this it looks like a double integral, families of functions, takes you back to the main area there, okay? Here's a quick reference guide here. I created a 5-minute video about this, so if you want to see a 5-minute summary of what I did, a 16-minute video if you have more time. This is how you get the linear equations and slope materials right now. All of those are live links except this one. I still need to do this one, okay, right here. But all these are live links. You are the only people in the world who have access to these right now. And if you have comments about them, I'd love to hear them, okay, especially if you use them with your students. What else? Coming later is going to be graphing trig functions. If you're an Inspire user, right here, you can get TI-Nspire files right here. There's a link to them. Here's the link to the grids. Here are the slides from what I just did, okay? These, they're in PDF, but you're welcome to go back over with them, and you can contact me with questions. And let me put up the last slide. This is the last slide, Mike. So here's my challenge to you. In the next 24 hours, if you could view at least 3 videos to see if this is something that can help you and also your students, I'd appreciate it. Only because it's one of those things, someday I'll go look at it and someday never comes. And so I think if you do it in the next 24 hours, you'll either say, yeah, this is really worthwhile, or this isn't for my kids, or this isn't for me, okay? So you've got my email for comments. You've got this. I need a couple more field testers for the trig section. If you're interested, just email me. It's a volunteer thing, whatever. So thank you very much for attending. I hope this is something that you can use. Otherwise, my 400, 500 hours was all for naught. So, Mike, back to you.
Thanks so much, Tom. We are excited that the T-Cubed International Conference is going to be virtual this year, and it comes to us over 3 different Saturdays, February 13th, 20th, and 27th. And as we mentioned a couple times tonight, by coming to this webinar, you are automatically registered to win a free conference registration. And tonight's lucky winner is Tony Fountain. Tony, congratulations. We'll be in touch over email in the next couple days to give you some more information. But we hope to see Tony as well as everyone else at the T-Cubed International Conference. To receive a certificate of attendance, as well as a link for the documents that were used tonight by Tom and myself, go ahead and click those links in the chat window. If those links aren't working for any reason, just hang tight. You'll automatically get a follow-up email within a couple days, and that follow-up email will contain links to the certificate, the documents, and also the recording. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Big thanks to Tom for putting in the 400 to 500 hours of time for this material to help all of our students. So, Tom, thanks so much.
Yep, sorry, I was muted. Thank you, Mike. And anybody, if you have a question that you didn't get answered, just email me. I will answer, promise.
And thanks, everyone, for joining us tonight. We hope to see you back online next week. Have a great night.